Hello everyone, welcome back to my channel. And today's video very interesting. Like we are going to understand again the concept of SVM, and sometime it is known as Optimal Separating Hyperplane in SVM. So you can see a very interesting diagram on the screen. We have two different classes of data points, a solid line in the middle and two parallel dash line on either side. But the important question is, why is this particular line called the optimal separating hyperplane? And what exactly are supporting vectors and maximum margin? Let us understand everything step by step with a practical example. First question is, what is a separating hyperplane? Suppose we have a classification problem with two classes. So in our diagram, the circles represent one class, while the triangle represents another class. Our objective is to find a boundary that separates these two lines. In a two-dimensional feature space, this boundary is simply a straight line. In higher dimensional space, we call it a hyperplane. The equation of the central hyperplane shown in the figure, that is y is equal to wx plus b is equal to 0. Here w represents again the weight vector and b represents the bias or intercept. As we all know, this is the actual meaning of this equation. And this hyperplane divides the feature space into two regions. Like I'm talking about, all those points on one side are similarly classified as one class, and points on other side are classified as the second class. But there is a problem. There can be many different lines that can separate the two classes correctly. So how do we select the best one? That is where the concept of maximum margin comes in. So look carefully at this diagram. The solid black line in the center, that is the support hyperplane. Let me select support hyperplane, and that is called optimal separating hyperplane. On either side we have two parallel dash line, and these are the margin boundaries. So the upper boundaries is generally represented as this equation, y is equal to wx plus b, and we are talking about plus 1 and minus 1. And the lower boundary is generally represented as minus 1, and the upper boundary is known as plus 1. The distance between these two lines, the normally hyperplane, that is called the margin between two lines. And the SVM tries to select the separating hyperplanes in such a way that this margin is as large as possible. So that's why we call it the maximum margin classifier. The basic idea is very simple. Don't just separate the classes, but separate them with a largest possible safety gap. We are talking about this one. This is our safety gap, and this generally helps the model generalize better when it encounters new unseen data. Now, let us focus on the most important points in this diagram. So we can see some highlighted points lying directly on the dash margin boundaries. So these are called support vectors. Notice something like interesting aspects. We don't need every training point to determine the optimal hyperplane. The points closest to the decision boundary and the most important because they determine the position of the maximum margin boundary. If these support vectors move, the optimal hyperplane can change. But If a data point is very far away from the boundaries, moving that point slightly may have little or no effect on the final decision boundary. So this is one of the most powerful idea behind SVM. So just remember, support vector are the critical training samples closest to the decision boundary that defines the margin and influence the optimal hyperplane. So real world company example, let us understand this with the practical company example. Imagine an e-commerce company wants to classify customers into two categories, high risk customer and low risk customers. Suppose the company used two features, x-axis and y-axis. It means x-axis numbers of previous late payment and y-axis is denoted by the number of successful transactions. Now imagine the most low risk customers are normally categorized in one region and high risk customers in another region. The company can use SVM to find a boundary between these two groups. So the central line is the decision boundary and the customer closest to these boundary become the support vector. And support vector then position the decision boundary so that the distance from the closest high risk and low risk customer is maximized. Why is this useful? Suppose a new customer enters the system. If the customer's data point falls clearly on one side of the optimal hyperplane, the model can confidently assign the corresponding class. But if the customer is very close to the decision boundary, the classification becomes more difficult. So therefore, maximizing the margin gives the classifier a wider separation between two classes, as you can see in this diagram. And the same principles can be applied in applications such as fraud detection, spam classification, medical diagnosis, customer classification, and image recognition. Now let us connect the diagram with the mathematics. The optimal separating hyperplane is WTX plus B is equal to 0. For the support vector, the two margin boundaries are WTX plus B is equal to plus 1 and WTX plus B is equal to minus 1. The distance between these two boundaries is known as margin is equal to 2 divided by W. And therefore, if you want to maximize the margin, we need to maximize or minimizing the magnitude of weight vector. The leads to the standard SVM optimization problem is generally categorized into 1.5. So subject to the appropriate classification constraints, the entire concept can be summarized mathematically as maximum margin that is known as the minimum 1.5. So we are just summarizing like optimal separating hyperplane is the decision boundary that separates two classes while providing the maximum possible margin. The two dashed lines represent the margin boundaries and the points lying closest to the boundaries, that is the support vector, and the distance between the two margin boundaries is the maximum margin that SVM tries to achieve. So remember the simple sequence, that is SVM first and find separating hyperplane number 2. Number 3, identify support vectors. Number 4, minimizing margins. And last, build a robust classifier. I hope this explanation made the concept of optimal separating hyperplane in SVM very clear and easy to understand. If you are generally like and any found this video very useful, please like it, share and subscribe also to my channel Kapil Joshi Tutorials. For more videos on machine learning, artificial intelligence and data science and research oriented concept, thank you so much and thank you for watching. Like I'm talking about the generalization of all those diagrams. Thank you so much.